Okay, class, today we're going to talk about Lewis diagrams and formal charges. In sophomore chem, you may have learned to draw Lewis dot structures, for example, for hydrogen monofluoride, using what I call the puzzle piece method. In that method, you drew the Lewis dot structures of each individual element. You figured out a way they would most likely bond, and then you would bring the electrons around in a way that they would bond. Then you would draw the bond in with the two dots next to one another. And finally, you would put a bond line for every shared pair. I call this the puzzle piece method because if you think about it, this electron sticking out like that is kind of like a jigsaw puzzle piece, whereas this fluorine here would have an outie like that, and then an innie here, and then the two pieces would fit together in the same manner as a jigsaw puzzle. This method is not a bad method for simple or small Lewis dot structures, but in AP Chem, we're going to be drawing some more complicated Lewis dot structures, and we need to learn a more versatile method. This method I call the electron placement method. Now, before we get started, I'd like to point out there's an excellent resource online. The link is in the Canvas assignment that goes along with the lecture notes. The link is to a Mr. Kent Chemistry website. It's an old school website, but don't let the look fool you. It has many short 1-minute Lewis dot structure videos where Mr. Kent goes through the drawing of Lewis dot structures for probably 30 or 40 different molecules, and he explains it very well. So if you need a little extra assistance, please check out Mr. Kent Chemistry. But now to my notes. The electron placement method is more versatile and will allow you to do more complicated Lewis dot structures, especially those where we might have what's called an expanded octet, where some elements can bond with more 8 electrons around the central atom. There are 4 steps in the electron placement method. The first one is extremely important, and we'll use the example of oxygen difluoride to illustrate these 4 steps. But the first step would be to count up the total number of valence electrons involved in the molecule. So you would know that oxygen has 6, each fluorine would have 7. That would be a total of 20 valence electrons. This is important because ultimately you will be placing 20 different valence electrons around these atoms that are going to bond together. Once you know the number of valence electrons, you're going to use what I call rules of thumb. These are guidelines that there are many exceptions to, but you have to start somewhere, and these rules of thumb or these guidelines are a great place to start. When you go to do a Lewis dot structure, you kind of have to decide what's going to be the central atom. And the way you do that is follow these rules. So first of all, as you see in the list, carbon likes to bond in the center. So if carbon is in your molecule, put carbons in the center. They also like to bond to themselves. We also know that halogens and hydrogen tend to form only one bond, and because of that, they are usually on the ends of a molecule. If your molecule doesn't contain carbon, hydrogen, or a halogen, the atom with the lower electronegativity tends to be what we call the central atom. And finally, you want to remember that elements in period 3 or lower can have more than an octet around them. And when one of those elements like chlorine or phosphorus or sulfur do bond with an expanded octet, they tend to be in the center. Now let's follow those rules for oxygen difluoride. Well, because fluorine is a halogen, I'm going to place that on the ends, and I'm going to place oxygen in the center. and I'm going to bond them together. Now this uses 4 out of the 20 valence electrons, so I'm left with 16 valence electrons that I still need to place in this structure. Next, we're going to do step 3, which says complete octets of the outside atoms by adding electrons to them in pairs. So of the 16 electrons, I'm going to add electrons. Notice now that the fluorines on the end have a complete octet. Also, I've used 12 of the 16 electrons, leaving me with 4 electrons to place from the original 20. Finally, the last step says place any remaining electrons on the central atom in pairs. At this point, you would check to see that all of the elements have an octet. If they don't, you would consider forming double or triple bonds. But in this case, fluorine, oxygen, and fluorine all have an octet. So we are done. Except for taking our shared pairs of electrons and turning them into a bond line. And since it was a single pair of shared electrons on either side, we would get a single bond line on each side. That is the final answer for the Lewis dot structure of oxygen difluoride. The first of our additional examples is going to be CH2O. Now, I've taken the liberty of doing the first 2 steps. I counted up the total number of valence electrons. There are 12. Carbon is involved in my molecule, so I placed it in the center, and then I placed the 2 hydrogens and the oxygens on the outside. And in this step, you make a single bond between each one of those atoms by placing 2 pairs of electrons between the atoms around the central atom. And you can see that we have used 6 of the 12 electrons. We still need to place 6 more. Now on to step 3. I need to complete the octet of my outside atoms by adding electrons to the outer atoms in pairs. Now you recall that hydrogen is happy with 2 electrons. So of the 6 remaining electrons, I'm going to place them around the oxygen outside atom in pairs. And we go 1, 2, 3, 4, 5, 6. At this point, I've used all of my remaining electrons. I've used all 12 valence electrons. And I'm going to move on to the second part of step 4. Well, my central atom does not have an octet. The carbon only has 6 electrons around it. And so you can look at the directions or the steps, and it says, if the central atom does not have an octet, form a double or triple bond by moving electrons in from the outside atom and placing them around the central atom, in which case we are going to to form a double bond in this case. And we'll take those electrons from that oxygen there, we'll move them into the share with carbon, and then we will erase these. It's best to do Lewis dot structures with a pencil. And then we see that the carbon has 8 electrons, oxygen has 8 electrons, hydrogen is happy with 2. Our Lewis dot structure is complete except for drawing in bond lines. Remember, for every shared pair, there's a bond line. And as you can see, I've done just that. Final answer, Lewis dot structure for CH2O, which actually you may have heard of this molecule. It is called formaldehyde. Okay, guys, next example, carbon monoxide. Again, I've taken the liberty of doing steps 1 and 2. Count up my valence electrons, I have 10. Well, I only have 2 atoms, and so they have to be placed next to one another. But if you have to decide which one of these is the, quote, central atom for step 3, because you're going to add electrons to the outer atoms, right? Remember, carbon likes to bond in the center. And so when we go to do step 3, to place some of these remaining 8 electrons, we're going to consider oxygen as the outer atom and carbon as the central atom. Again, I took the liberty of doing this step. So here are the 6 electrons around oxygen to make oxygen have an octet. I no longer have 8 electrons left. I now have 2 electrons left, which I will place on the carbon, because the next step, step 4, says place remaining electrons on the central atom. Now I'm on the second half of step 4. I look to see, do all my atoms have an octet after I've placed my remaining electrons on the central atom. Well, carbon does not have an octet, so I'm going to move some pairs of electrons in from the outside atom, which in this case is oxygen. I move them in pairs, and you can probably see in this case I need to move 2 pairs in. So I've redrawn my carbon monoxide with the 3 shared pairs in between. And now I'm ready to do the final Lewis dot structure, because everyone has an octet. Carbon has 8, oxygen has 8. Again, all that remains is I draw in a bond line for each shared pair. This is a triple bond, or bond order 3, and I leave the remaining unshared electrons, sometimes called lone pairs, on the outside. Final answer, carbon monoxide. Sulfur hexafluoride. Now remember, sulfur is in row 3. It can have an expanded octet. Remember these, because it's going to have 6 fluorines bonded around it. Again, remember, because halogens tend to bond around the outside in most cases. So the sulfur will be in the middle. It's the element with the expanded octet, also the element with the lowest electronegativity, and it's not a halogen. So I've done step 1 and 2, placed sulfur in the middle, made a single bond between all of the fluorines and the sulfur, and that has used 12 electrons, and so I still have 36 electrons to place. All right, in blue, I've placed the 30, it turns out to be 36 electrons on those fluorines, 6 electrons per fluorine. Sulfur has more than an octet. Each fluorine has an octet, and I've run out of electrons, and so I'm basically done. Again, all that remains is for every single shared pair around the sulfur, I've drawn a bond line. And again, this is a case of an expanded octet. This would be an octahedral geometry. Okay, finally, let's look at hypochlorite ion. Now, this is a polyatomic ion and has a negative charge. When we count up our valence electrons, we have 7 for chlorine, 6 for oxygen. You add in 1 more for the, quote, stolen electron that hypochlorite ion has picked up. Again, here's step 2. I take my chlorine, my oxygen. There's only 2 atoms. They have to be next to one another. I single bond them. I've placed 2 electrons. I now have 12 left. In this case, chlorine with the lower electronegativity will be considered the central atom. Oxygen with the higher electronegativity, I'm going to place electrons around it, the quote, outside atom. Doesn't really matter in this case, but 6 there. That leaves me 6. I'm going to put them on the other atom. I now have no electrons left. Chlorine has an octet. Oxygen has an octet. I rewrote this with the bond line. Now, this is a polyatomic ion. You may have learned, sophomore chem, that all ions, when their Lewis dot structures are complete, must be written with brackets around them and the charge of that ion outside the brackets. So to complete this polyatomic ions Lewis dot structure, I need to put brackets around it, put the charge, final answer for hypochlorite ion. Okay guys, now you're pretty much ready to do Lewis dot structures. Stay tuned for the next video, which will be on formal charge.